Hello students. This video was intended for you to watch at home, so I'm going to go a little bit faster than I do in class because you have the ability to pause every section of the video, every part, to take notes and to catch up if you need to. Okay, so you already just saw what my screen said, but we are going to learn how to, in this video, construct and calculate confidence intervals for variances, that's sigma squared, and standard deviations, that's sigma. Now again, when we write sigma squared as opposed to s sub x squared, and sigma as opposed to s sub x, we were talking about the population standard deviation slash variance. That is the variance of the whole population, the standard deviation of the whole population. So again, we're using our sample, say standard deviation s sub x, as an unbiased estimator and a point estimate of the actual standard deviation of the population. So like before, we're going to get an interval because we know that our one sample, our one standard deviation from the sample is not going to be a perfect representation of the actual population. Okay, so I'm going to start with the conditions, and the conditions are the same for a t interval. That is, number one, the sample has to be random. If you don't have a random sample, it's not a fair representation of the population, and your estimate is going to be biased and useless. Okay, the normal condition, just like a t interval. Sorry, a lot came up at the screen all at once, but let's just look at the normal condition right now. Either, and this is exactly the same, this is exactly the same as a t-distribution. Either the population is normal to start with, and that had to been given in the problem, or if the sample size is over 30, both 1 and 2 are results from the central limit theorem. Number 3, in case it doesn't tell you any of that, so it doesn't tell you that the population is normal, the sample size is under 30, you should make some kind of plot of the data. Usually I just recommend making a histogram or a box plot from your calculator, and it should show no strong skewedness or outliers. Okay, we're going to have two confidence intervals here. One is for the population variance, sigma squared, and the next one is going to be for the standard deviation. But you just use one, take the square root to get the other. Okay, so the confidence interval for the variance. So this is going to be a little bit different than our confidence intervals for means and proportions. And the reason why is because we were using z and t distributions which were symmetric, so we essentially added the same margin of error to both sides. That's not going to be the case now for variances and standard deviations, since the chi-square distribution is not symmetric. I'm going to need my two different critical values of my chi-squared that we went into for the last lesson. So your lower, you can consider this number here your lower part of the confidence interval. It's going to be n minus 1 times s sub x squared over the critical value of chi-squared on the right, and then your upper value is going to be n minus 1 times this variance, that's s sub x squared from your sample divided by the left critical value. And notice how when we write this, what we're saying is that, hey, the actual population variance should be in there. Of course, we're not 100% certain, but depending on the confidence level, we're 90%, 95%, 99% certain that the actual population variance should be in there. So typically this is step number 1. Usually we want to get the standard deviation, and all I have to do essentially is just take the square root of the left side and the right side, going to the next screen now, to get the standard deviation of the population. Oops, what's going on? There we go. So for the standard deviation, since the standard deviation is the square root of the variance, I simply square root left and right side. Okay, you ready to try one? Let's do it. Okay, estimate the population variance and the standard deviation of the population from the following simple random sample of 10 SAT scores. And let's check the conditions in the meantime. So we have 10 SAT scores: 920, 1050, 890, 1010, 1090, 1000, 1080, 1040, 930. Not a ton of spread for SAT scores, right? Usually you know a few people who score, I don't know, 12, 1300. Smarty pantses, right? Okay, so let's start out with the conditions. The conditions were is this random? That's always condition number one. Yeah, SRS, and if you forgot what SRS is, that's a simple random sample. That's the best kind of random sample that we got. Next condition is the normal condition. So we ask ourselves, question number one does it say, I actually start out with question number one, is the sample size over 30? Nope, it's not. Question number two, does it tell me in the problem that the population is normal? Oh, it doesn't. So we are left with just a bunch of raw data. So what we're going to need to do, and you should probably pause the video, do this along with me, is pause the video, put those numbers up here into L1 in your calculator, the whole list of 10 numbers, and make a histogram. Okay, my histogram may not look exactly like your histogram, mostly because I'm not using my calculator. I am using R right now because I'm at home. But I got my SAT scores kind of bottomed out at 850, went up to 1100. And again, when I look at this histogram, I'm looking for, I'm pretty much looking for anything that's not normal. And although this isn't 100% mound-shaped, it's slightly skewed left, but it's not strongly skewed left. So I'm just going to call this no outliers and not strongly skewed. Weakly skewed, okay, but we don't want strongly skewed, so it checks out. Okay, next part of this problem, I needed to go back to my calculator, and I need one var stats. And I could just as easily also estimate the true average SAT score using a t-distribution, the true mean. That's using a confidence interval for x for mu that we learned in 6.2, but we're going to do the standard deviation. So what I need from this, from one var stats right now, is essentially two things, or we could just get away with one. And again, I apologize that I don't have my calculator here, but we need the variance, which I got as this number here, 3,937, and then the standard deviation should be the square root of that at 62.5. Next thing I need for my formula, and again, this is going to be my formula right here that I need, is I need my critical values of chi-squared. I'm going to go to the back of the book to table D to find that right now. And you know what? We didn't even mention a confidence level, did we? So let's go ahead and mention a confidence level here and say this is for 90, what do you want to use? Let's use 95%, sorry. Sorry, that's up there, not up there. So, and often this could be the case in a problem that it doesn't tell you which confidence level to use. At that point, it's up to you to make it up. Traditionally, 95% is just a great number to use. It's fairly accurate, but not overly accurate, like a 99% confidence interval. So see if you can recall how to find the two critical values of chi-squared. Pause the video for a minute and go back to your book and find them. Okay, so how many degrees freedom did we have? Well, the sample size was 10, so we have 9 degrees freedom. And for a 95% confidence level, again, we're going to go to the back of the book on table B, or Appendix B, Table 6, excuse me. And we are going to, okay, and it again helps to draw this out, so I'm going to draw out a little chi-squared curve here. And go, okay, if I'm looking for the middle 95%, that's going to leave 0.25% there. That's my middle 95%, and I'm sorry, when I meant 2.5% or 0.025 in terms of area, and likewise on the right side. So, what do I need to do? Go into the back of the book, and I could start out just looking under 0.025. That's going to give me my value on the left. Now, I would like to mention your book. I got confused a little bit on the book because if you look on the table, it's got that chi-squared to the left and the chi-squared on the right mixed up again. Whatever you call them, hopefully you can find each. Okay, I got 19.02. It's a decimal point. 19.0. Sorry, where was that? 23. Hopefully you found that as well. And that was the easier one using 9 degrees freedom. And now, how do I find the chi-squared value on the right? Well, again, this is going to be a little tricky, but how much area is to the right of there? Well, it's not only this 95%, but it's also this 0.25%. So total, that's going to make 97.5%. And I look under that number, and I got 2.700. Alright, now I got just about everything I need for my confidence interval. And I'm going to leave it up to you how you want to solve this. Here's maybe an easier way of solving this. Okay, this first one is for the variance. And if you looked at the formula that we had in the book, you can use this as well, and this is already essentially in interval form. So in this case, this whole thing is 10 minus 1 times s of x squared, which we had up there, 3937.88. And I apologize, I'm going to have to go to the next slide. Okay, so I know that just magically appeared, but I just was rewriting some of the work there. So again, on the left side, it's going to be n minus 1. Sample size was 10 times the sample variance. That number, 3,937.778, we had calculated before. Excuse me. Now you might look at this and go, wait a minute, why? Which number goes under what? Typically, the bigger value, in this case 19.03, is going to go on the left. And it might seem a little counterintuitive, but remember, we're dividing by the bigger number. If we divide by a bigger number, this number on the left is going to get smaller. I'm just going to pause the video myself and put these numbers in the calculator and magically get my answers. Okay, so on the left I got 1863.008, and on the right I got 13125.93. Now this is again for the variance sigma squared. So you might be looking at these numbers and going, wow, these are big numbers, right? We're used to standard deviations not being quite that gnarly, but a couple things we have to consider. We're going to square root this in just a second to get the standard deviation. And second of all, SAT scores typically have standard deviations in the hundreds because a lot of the scores, right, if the average is 1,000, plenty of people get 1,100, 1,200, 800, 900. So you'd expect a little bit bigger of a standard deviation. Okay, last thing I'm doing to get my standard deviation is I'm just going to simply square root both sides. And after square rooting both sides, and again I say square rooting both sides because all I did in my calculator was I took the square root of this number to get that, and the square root of that number to get that for my standard deviation. And I get that I am 95% confident that the true standard deviation of SAT tests are between 43.16 and 114.568 SAT points. I know this is fairly complicated, a lot of steps to these problems, but again, hopefully you have this video, you can go back to it whenever you want, you got good notes, and happy studying. Thanks, students.